So, we're going to begin now, back into our conversation about the energy contents. So, we left off introducing the third law. So, recap. First law is what? If you have to sort of frame it, what would you say if you had to sort of describe in your own words, what does the first law really say? Yeah, the conservation energy, right? Conservation of energy is about, remember, if we have a process is going to be some give and take between heat and work, and what we're saying is the overall energy content must be conserved, right? Heat can be converted to work and vice versa, but overall the delta E or the delta U of a process, the total internal energy change, can be recapitulated by just measuring how much energy went where, right? What was the second law? What did you remember? What do we call the second law? And this is what we discussed quite heavily last time. Yeah, entropy must increase. Delta S of the universe must be equal to or greater than zero. This is our law of diminishing returns, right? This is why perpetual motion doesn't work. This is why the universe is basically built in such a way that we're always going to be sort of moving forward. And yeah, you will never get out all the energy that you put in. This is what happens with irreversible processes. Sarah, do you have a question? Okay. Last, we have our third law. The third law, as we dictate here, this is a way that what we say is we're going to describe the universe in terms of its entropy content based against this concept of temperature, right? This is where Boltzmann made a distribution saying, look, if we can think of entropy as generally this way that we're binning or moving energy around, ways of distributing or passing energy around a system. That's how we get this idea of spontaneity, right? Spontaneous processes are where the entropy is increasing, and what we're really saying there is if I have a concentration of energy, lots of energy associated with just a couple of molecules, and they're surrounded by a lot of molecules that have less energy, energy will move from where it's concentrated to where it's less concentrated. This overall evening or smoothing out of energy. We generally refer to this as disorder, chaos, but the concept really is about this smoothing out or evening out of both matter and energy throughout a system, right? If we put a dollop of cream in black coffee and do not stir it, spontaneously it will generally by diffusion even out to create a homogeneous solution over time, right? So that's what we're saying. The second law is the third law really says that, okay, if we need to quantify this, we need to define some state or some place in sort of the whole sphere of existence where we can define energy as equal to zero. This provides a reference point for us to do measurements in order to look at how much disorder, energy content, or distribution is in a system. This is, we discussed last time, W, the number of microstates within a macrostate. That's just really saying that if we decrease the temperature, we lower the ways in which energy can be distributed, and we put all the energy in one single state, a perfect crystalline state. And that's what we define as our T equals 0 on the Kelvin cycle, or the Kelvin scale. If we lower the temperature to temperature equals 0, this is how we define absolute zero. All molecular motion stops. You get an infinite perfect crystalline lattice of any matter. And that's where we say entropy is 0 at that point. And having that as a reference point is useful because now we can measure entropy up from that point. It also allows us to extrapolate down and say where temperature is 0 on this point. Would a heterogeneous mixture have potential energy? In a way, right? What you're really saying is, if we start off a system where the distribution is highly unequal, right? If it's concentrated versus an area where there's a lot that isn't, we will have a spontaneous force or spontaneous presence where that mixing will occur without us having to do anything else. Once we start the system, let go and let time flow, time will allow that sort of mixing to kind of happen. So you're right. It's you can think of it where, remember, this is why we define entropy in this way. It's our way of sort of putting a quantification down and saying of the processes that are possible, which ones will happen spontaneously, which ones are set up to sort of follow the normal flow of both energy and time. So once we've defined this third law, that temperature equals 0, the S, the entropy in a system is 0, we can define now the standard molar entropy of a system. And this is analogous. Think of it in the same sort of category as our delta H of formation, right? Remember, what was special about a delta H of formation? We had a couple of caveats, criterias. Delta H of formation was what? If I had a balanced chemical equation, How would I describe the delta H of formation of any molecule? How would I write the balanced chemical equation, for example, of formation of water, right? H2O. Yeah, it's the delta H final minus initial. That's partly that. That is part of it, right? But if I had to draw the balanced chemical equation describing the delta H of formation of water, it's going to be the made from elements in their standard state. So again, if we were talking about water, we need hydrogen and oxygen. It's not just H and O, it's H2 and O2, the diatomic gases, so they both must be in gas state. And then we balance it off based on the number of atoms we're going to need. That's going to be 1 H2 and half of an O2 in gas state. We also say that any element in their standard state, their delta H of formation is 0, which allows us to have this reference value, the delta H of formation of any molecule referenced against these elements in their standard state. What we're talking about here is we're saying the standard molar entropy is going to be forming this substance. What's the absolute entropy of this substance in its standard state as referenced against our 0 value. Once again, just to kind of quantify things, entropy increases as your states increase, right? If you have a solid will change with temperature, but its overall slope, how much entropy we introduce to a system, is going to be lower than the liquids. The slope of change with temperature for liquids is higher, mainly because there's higher molecular motion there. Having something that is a more mobile material, if matter is easier to move, it's easier to distribute, there's more ways of sort of orienting things. And again, you can think about that like in a solid, everything is quite rigid. A crystalline solid is very well ordered, and there's not a lot of options to sort of move atoms around. In a liquid, there's many different configurations of where those atoms can point, and every one of them is consistent of one microstate, one way to sort of distribute that energy. As a gas, you have even more degrees of freedom. Things can now expand, get away from each other, distribute that energy over a large volume as well. And each time we go through a phase transition, there's a jump in entropy as we move from solid to liquid, where there's no corresponding change in temperature. So those are the special transitions that we're going to talk a little bit about more too. There's calculations we can do and things we can know about there because the delta H isn't changing, or so delta temperature is not changing. What is TM and TB? What do you guys think? TM, going from solid to liquid, TB, liquid to gas. What do you guys think? Yeah, melting temperature and boiling temperature. That's right. It's the transitions we move between those two. It means also going other way. Gas to liquid, we would call it T condensation. Liquid to solid would be what? What would you call that? If we were referencing saying I went from a liquid to solid, the temperature at which that happens, fusion or freezing. Yep, that's right. All right, so now that we know these ones, and we've got this idea of these reference ones, we can apply the same thing we talked about with Hess's law to figure out the delta S for any process. And this is exactly the same concept. If we know the S, the entropy in the final state, we know the entropy in the initial state, we can calculate the delta S. And provided we're talking about standard enthalpies for a molecule, we can do this, again, lookup table for what is the standard entropy of that molecule.
Sorry, could you say that?
In its standard state. Siri's deciding to jump into the lecture today. It happens a lot because of how my S's sound. Anyway, final minus initial. It's the same overall sort of calculation that we've done before. So let's apply it. If we had this equation, we're taking iron plus oxygen to make Fe2O3. And we're asked to find the delta S of formation under standard conditions, the delta S naught at 298. We're provided the S naught, the standard entropies of these individual chemicals. Now, two things I want you to notice. Look at the units for entropy. Do you remember what the units for enthalpy was? What was our unit for enthalpy generally before? For delta S or delta H? Not quite the same. There's one thing that's different here. Yeah, enthalpy, delta H or H, is a unit of energy heat. It's kilojoules or joules per mole, right? It's energy over molar value. Quickly, intensive, extensive. If it's kilojoules per mole, intensive or extensive? Yeah, it's intensive, right? We're normalizing based on the size of the system. Look at these guys. Units are joules, energy, per mole, but what else is in the denominator? Temperature, right? Entropy values, remember, since entropy depends on temperature, how much entropy is in a system will be contingent on what temperature you're at. That's why it has this temperature dependent quantity, right? So it has this extra part. It's one of the things to look for. You're dealing with an entropy value if you have these joules, moles, and a temperature quantity built into it too, right? So it's normalized against the temperature in which the reference is happening. Next thing too, look at size. What did we say? What type or state of matter has a larger entropy, solid, liquid, or gas? Yeah, and look at your values here. Does this gel? Look at the S's for each of them. Which one's huge? Oxygen, right? Iron is a solid, oxygen is a gas, FeO2 solid, right? It is tenfold bigger in terms of magnitude than the others. So one more thing I want to point out too is these are joules per mole. Generally, delta H's, the heat values we talk about, remember the ones we calculated for things like the bombardier beetle? Those are in kilojoules per mole. Those are 1,000 times bigger, and this is what you see too. The delta H values in terms of their general magnitude is going to be larger because they're generally on a kilojoule scale versus entropy, still a unit of energy over temperature, but it is actually usually a factor smaller, right? We're usually joules per mole instead of kilojoules per mole. So, does anybody recognize this equation too? Where have you seen, or what is this describing? Iron, oxygen making Fe2O. Yeah, rusting. This is an oxidation, right? This is just like burning something. It just happens to be an inorganic material. If you grew up in the prairies and you've had salt on the roads for 9 months of the year because of snow, this happens a lot to your car, right? So what do you know about this process? Spontaneous, non-spontaneous, would you say? Does it happen? Yeah, this is something that will occur, right? Like you are familiar with this. If we mix oxygen with iron, this process can happen once the activation energy is achieved. The rates may be different, but it definitely occurs. This is all good. So let's look at the actual energy for this system. There's a couple things I want to point out as we go through. All right, so calculation on this, we are taking 2 molecules of iron as a solid, 3/2 oxygen as a gas, and it's making iron oxide. Okay, so the calculation we need to do, it is, again, products, the overall delta S for this reaction will equal to our products, which is our Fe2O3, and that's 87.40, minus the sum of all our starting materials. That's going to be 2 times 27.28 plus 3/2 times 205.1. Putting all that together, we get 87.40 minus 362.21. And finishing this off, we get a negative 274.81 joules per degree Kelvin mole. Okay, so there's a couple things I want to point out here. Notice we are starting with iron in its solid state. Is that the element in its standard state? Iron, solid, monatomic, yeah. So why is the delta S not 0? No, because it's delta S, right? Which would be 0? Iron, pure iron, solid state, yeah, the heat of formation will be 0. We are talking entropy. Entropy is reference to that molecule at 0 degrees Kelvin. We are talking, here we're discussing a reaction of this molecule at 298 degrees Kelvin, standard conditions. The units of entropy here are joules per degree per mole, right? So it doesn't have to be 0. So don't look at this and go, oh yeah, no problem. Iron, standard state, delta S is 0. No, that is delta H. Delta S have values as long as they're above 0 degrees Kelvin. That's the first. Okay, and same thing with oxygen, right? Yes, it's a gas, but once again, it still has a value. The magnitudes, we were talking about that before, gases should be bigger than solids, makes sense. If you look at the overall process here, remember we talked about this in terms of magnitude before, looking at this reaction, what's happening to the overall number of moles of gas? Are they increasing or decreasing as we move from starting material to products? They are decreasing. So does the fact that this reaction shows a delta S of reaction negative, is that kosher? Is that good? Does that match what we should expect? Yeah, well, no, it does. That's right. We are starting with more gas. We're getting less gas. We're destroying the number of moles of gas. That's good. That is exactly what we should look for. Yes, that's all good. So the two things I want to point out, just because an element is in its standard state, we're talking delta S, does not need to be 0. Don't throw that value out. Number 2, we are starting with gas. We are making no moles of gas. That we would expect the delta S to be negative, and that means we have done this. Yes, this is just like our sort of gut check that we talked about for endo and exothermic reactions. Okay, so we just talked about this being spontaneous. Delta S of reaction is negative. What seems wrong about this? Does this bother anybody? We just calculated delta S naught of reaction is negative, but we said, but this is a spontaneous process. What is going on? Yeah, enthalpy is not included. That's part of it. Remember, what does it mean if we are talking entropy and we're saying it is a spontaneous process? Spontaneous means what in terms of entropy? Increase in entropy, yes, of what? The universe, right? We said that the delta S of the universe must be greater than or equal to 0, right? This is not delta S of the universe. This is the delta S of the reaction. We're looking at a piece of the puzzle, right? This is only what we're talking about in terms of the entropy change, focusing only on iron and oxygen turning into Fe2O3. But we know that this has to be a spontaneous process based on measurements and our experience. What does that mean about the delta S? How do we rationalize these two? Delta S universe is negative, or sorry, delta S reaction is negative, but we know it's spontaneous from experience, therefore delta S universe should be positive. Where's the missing quantity? How do we rectify these two? Yes, the delta S of the surroundings must be positive. And what do we know about the magnitude? What is the value, probably, of the delta S of the surroundings? It's positive. Yeah, it's probably going to be bigger than this number, right? So what we're saying there is that it's the combination of the two. This is the reaction. This is the system. Yes, the system is negative, but just looking at the delta S alone does not give us a perspective on spontaneity. We must look back at delta S of the universe. And unfortunately, that's a kind of hard thing to do. This is why we have to move to our delta G values. But that's the thing to kind of focus on here. None of this fits outside of what we expect. There's gas going down, should be negative, yet being spontaneous. That's because we're not talking about delta S of the system. We have to talk about delta S of the universe. That just means delta S of the surroundings must be larger and positive for this to happen. It's the composition of the two. So this is our overcalculation written out, the sum of the products minus the sum of the starting materials, final minus initial. And we just bring in our stoichiometric quantities too. So we have 2 moles of iron, 3.5 moles of oxygen. We bring the two together. All right. And again, it bears going through this and looking at both the quantity, magnitude, so it sort of fits with our gut decisions about what these values mean in terms of their definitions. Yeah, it has to at least be equal to that value for everything to be 0. Now again, if the delta S of the universe was equal to 0, that is a very, very special case that we're going to talk about just here, right? If delta S of the universe was 0 for a process, what we're really saying is that is that perfect, idealized, reversible case where everything in that process was perfectly in equilibrium the entire time the process was happening. For a chemical reaction, that is really difficult to do. What we mean is that oxidation we just talked about, iron, oxygen, right? We're saying that nothing can leave the system. No energy can possibly leave. It would have to be perfectly in equilibrium balance as every molecule was happening. And we know, again, by experience, As you oxidize iron, it changes form, it flakes, it falls apart. Creating a system that perfectly matches in equilibrium is a very challenging thing to do because we have to keep track of where the mass and energy actually is. The best thing we can do, and again, think back to when we first started talking about first law. What is a system that we talked about, physical, that we can have both an irreversible and a reversible process associated with it? Yeah, the pistons. If we did isothermal slow compression or slow expansion, that would be an example of a system that maintains equilibrium as it's changing. It's always the delta T is 0 at all points to that. We have our isothermal path, and in that case, we can apply this one further case here. In this case here, if we have the special case under constant temperature, like that piston, where it is always obeying that constant temperature, it is a reversible process. The heat associated with that reversible process, if we know it, we know the heat associated divided by the temperature at which the process happens. That is another way for us to calculate the delta S of that process. And again, it only really works in this specific one. Yeah, the first one is the overall derivative one. That's our calculus definition. The special case where we say that it's happening at a constant temperature, the dt is equal to 0. We've got this other one here where the reversible heat is a constant value for that one specific process. Again, this applies only for reversible systems, and we really only have two that we can talk about. The piston is one, an isothermal process where we've got this nice reversible energy. That is possible. Again, if we set the system up perfectly, we can get close to it. And that's where measuring the heat during that reversible compression or expansion will allow us to measure the delta S that was happening for that. What is another example of this closest here? A reversible process happening at a constant temperature where only heat is moving in and out of that system. Can you think of something else that might meet these type of criteria? It has to have no change in temperature, heat is involved, might be reversible. What's another example you could think of? Now, a balloon is a little tricky because we've got, again, but that's kind of like a piston, right? You can maybe think about that. Calorimeter, maybe. I'm thinking, remember, in a calorimeter, we're measuring a delta T in order to measure that heat change, right? Inside, we can say maybe all of it's contained, but there's still a temperature change that's involved during that. Like a bomb calorimeter specifically. Yeah, phase change, exactly. Melting is a really good example of this. There's very little changes in volume, usually as long as there's not major changes in density. The heat that's involved with melting something at its melting point. If you're at Tm and you're undergoing a phase change, that entire time going from a solid to a liquid where you are at the melting temperature can be construed as another constant temperature process where we can measure the heat associated with fusion or melting. And again, the heat of that phase change process under constant temperature could be a way to measure the delta S of it. When we go back to this, that jump, that's kind of how we get that jump. We measure the magnitude here by saying it is a constant temperature process. What's the delta S going from solid to liquid during that point? By measuring the heat that is involved in that phase change process, right? So this is a useful energy, one way to do it too. So we have two ways now of calculating the delta S. Either I know my final and my initial, that's one way, that's using our standard enthalpy values. Or the second one is, as long as I'm dealing with this constant temperature condition, I can analytically calculate it knowing the reversible heat, or the heat that is involved with this reversible process. Okay? So, let's put signs to things. If you have a phase change now, this is the other one we described, phase change at constant pressure, what do you think is going to happen to this sign of delta H and delta S? So imagine it's ice. We're melting ice at T equals 0, so the whole system as T is equal to 0. P is at 1 atmosphere, so we're at constant pressure while this happens. Now remember, that's talking about the work that might be involved in this. What's the sign of delta H if we go from a melting process? Where do you think the heat is going? In or out of the system? Right? So what should the sign for delta H be with respect to the system? The delta H, yeah, we're going to be adding heat into the system. We expect that to be positive. What about the delta S? We're going from phase change, right, it's going to be a negative value, right? What's going to happen? Wait, phase change, delta S? If you're going from a solid to a liquid, it's getting more disordered, right? We're going from an ordered solid to a more disordered solid, so also positive. So under constant pressure conditions, right, if we were doing a phase change under constant pressure conditions, there's one more thing else to remember about the heat that's associated there. Remember, we called that QP. That was our calorimetry section. If I do a phase change or if I do any process under constant pressure conditions, I'm actually measuring the heat during that constant pressure. That is my delta H, my enthalpy value for this one. What was the other Q value we did? There's QP is constant pressure heat. What's the other one that we talked about? Back to calorimetry. QV, right? What was special about QV? QP equals delta H. QV equals what one? Yeah, that's constant volume. There's no work. QV equals what value, sign, letter? Yeah, delta E, the total internal energy, right? Remember the difference between these two, QP, constant pressure, there could be work, it might be small, but that's our delta H. QV, constant volume, work has to be equal to 0. All the delta E is equal to QV. The heat associated is 100% of the internal energy change. That's our bomb calorimeter. And then delta S, that's just what we've been talking through now. Phase changes as we move into higher orders of matter, right? Solid, liquid to gas, we're going to be increasing the entropy as we go through this because of greater molecular motion. All right, so this is where we get to our last problem. Like we said, to really be able to, if we don't know anything about a system, never seen it, just seen it on paper, trying to predict it, the problem we run into is we need to know the sign of the delta S for the universe. Now, as the rusting example we just gave you, we know the sign of the delta S of the system. We don't know the delta S for the environment, whatever's going on around it. So as a result of that, it's difficult to predict it without other information. So we need to actually go back and use something else. This is where we focus on what's now called the Gibbs free energy. This is where we bring it together. What's nice about the Gibbs free energy is it allows us to do everything we've talked about, but it brings back in delta H. It allows us to focus only on the system and still make an analytical quantity or a value that says, is this thing spontaneous? And more importantly, it adds one more thing to this. It's not just, is this spontaneous? We're adding one more sort of value. Is it spontaneous under the temperature or conditions we are currently looking at? There are some processes that are always going to be spontaneous based on how the values of both delta H and delta S are. However, the Gibbs free energy, remember what's the big equation for Gibbs free energy? Delta G equals, two more terms. Delta G equals delta H, yep, plus T delta S, or minus T delta S, right? Exactly. So what we've got is our delta H and delta S quantities we're going to start to relate in. That's our heat and our entropy and our enthalpy. But it also has this temperature value, the temperature where that process is actually happening. It becomes a predictive tool we can use to look at predicting beyond this. So the general one we're saying for any individual state, if nothing is changing, at equilibrium, just one of our values, we can say that the Gibbs free energy of a system is equal to a sum. It's a term between the entropy value and the enthalpy value, H minus TS. Now, if we do a process, we change something, we move from some heat or some enthalpy and entropy value to a new entropy and enthalpy value, and if that process happens under constant temperature conditions, the delta T is equal to 0. T does not change. So we can rewrite this saying that for some process, the free energy change, delta G, can be written or derived as the delta H, the change in enthalpy, minus T delta S, where T is constant for that process that we're changing it. So this is useful. There's one big caveat that we add to this too. Does anybody know that what also has to be true if this is if we're trying to apply this? We're saying, okay, temperature is not going to change. What about the value of, well, pressure can sort of be, usually we put that under standard 2. The magnitude or value of delta H and delta S had better not change with temperature 2, right? I mean, how big that jump from starting material to product is had better be constant over a wide range of temperatures. Now, the good news is, for a lot of temperatures or a lot of processes, this holds. If we're talking about something sort of our world of, minus 10 to about 120, that range of reality, This is a pretty good approximation. What starts to break down, though, if we start looking at astrostellar type things, what's happening in fusion, really those far edges of chemical matter, these thermodynamic laws definitely fall apart. The delta H and delta S under extreme conditions of some like internal energy combustion, things like that, they do change. But for most of what we're going to be dealing with, we make the assumption that if I know the delta H from some process, and I know the delta S from some process, I can calculate the delta G for that process at a constant temperature. Quickly again, we just talked about it. Give me two ways I could calculate the delta H for any process. If I gave you just a reaction, what's one way you could pull the delta H? What's a way or value or a method that we could use to calculate the delta H that I did not know? You can look up values, anything else. Yeah, formation reactions, that's a good one. What else? Hess's law, perfect. One more, the calorimetry, right? Delta H is equal to QP. If I could measure the heat under constant pressure. Those are all great. Delta S, I got two ways. We just talked about them, which is one. Delta S I could use kind of like Hess's law again, right? Final minus initial. If I had my standard entropy values, I could measure final minus initial. I could measure the delta S. What's another way? Yeah, Q rev over T. If it happens to be a reversible process we're talking about, and I measured the reversible heat, Q rev over T gives me that delta S value. That's right. And those allow me to calculate delta G, and vice versa. If I have delta G, something else, I can actually pull these other values as well too. So we actually use these things in sort of this concert, in this circuit. Depending on for certain systems, sometimes it's easier to measure or approximate a delta G value. Sometimes it's easier to measure to approximate a delta H. Delta S is usually one of those ones that unless we've got really good analytical values from something else, it's usually the one that we're fitting or solving because we can actually get ways of analytically measuring delta G and delta S by other ways. So what it means is we've got this grid now. Something is considered spontaneous if the sign of the universe, delta S, remember, is what? Positive or negative? Right, it has to be spontaneous. Delta S universe had better be, positive, not negative. The delta S of the universe has to be positive. If it's equilibrium, what's the value? Remember, this is a perfect equilibrium system. Delta S of the universe is, that's 0. Non-spontaneous or doesn't happen is what sign? Negative, that's right. Because there's interrelationship, remember, the overall equation we just looked at, delta G is equal to delta H minus T delta S. There's an inverse relationship between the signs. A positive value that has a positive delta S in the universe would have a negative delta G for the system. And vice versa, a negative delta S for the universe will have a positive delta G value. So what we're doing now is we're transposing this and saying as long as I can look at what happens to the sign of delta G for my system under constant pressure, constant temperature, then I can say something about if this process is spontaneous or not. It allows me to put the entire focus on the reaction instead of having to try and fully measure the system around, or sort of the surroundings around the system as well. It makes the analytical part of it much easier. But what happens from this, though, is there's a consequence, right? There are 4 basic combinations. Think of this like binary logic, right? Depending on the sign and magnitude of delta H and delta S, we can have 4 possible consequences. It could be spontaneous all the time. It could be non-spontaneous all the time. Or it might depend on both the sign of things like the value of delta H, delta S, or its temperature. So what does Gibbs free energy actually measure? It is think of it as a quantified value that's taking together both the driving force of the reaction as determined by entropy and the driving force of the reaction as determined by enthalpy. Let's just go through this one here, and what you'll see, what we kind of saying is, look, if the rule is for some reaction, you've got to have a price to pay. Much like we talked about energy in unit quantities of heat and work, if a reaction's going to go, it's going to be spontaneous at some temperature, if it's happening under those conditions. What we're saying is the delta G of that specific condition has to be a negative value. So if you look at these 4, which one of these combinations, plus, minus, plus, plus, will the delta G always, always, always be negative? Whoops. Let me go back to my iPad. Yeah, so if we look at these, right, and I'm saying, okay, here's my delta H, here's my delta S, the resultant sign of delta G that I can map out here will depend. If the delta H is negative and the delta S is positive, no matter what the temperature is, this will always be negative all the time. What I mean is for all values of T at any temperature, because the delta H is negative, the delta S is positive, it doesn't matter how big my temperature is, the delta G must always be negative. We say in this case, this is always spontaneous. Right? What about the other side? When will it never, ever be spontaneous, no matter how big or how small the temperature value is? Yeah, if the delta H is positive, the delta S is negative, we've got two things that are pushing against this. The delta G must be positive for all temperatures, which means it is non-spontaneous. All it means is for the two states that we're considering, the thermodynamic parameters, both the enthalpy and entropy, are working against us. We cannot do that reaction on the current as it's currently set. There must be some other way that this is set up so that we've got a different, we'd have to do something else completely. But what it means is there's no way I can pick a temperature based on these two values and have this thing have a positive delta G. Okay, now we've got two more cases. If we had sort of the middle one, let's say the delta H is negative and the delta S is negative. First of all, delta H is negative. What do I say about that? I have a name or special name for a delta H is negative process. We call it what? If the delta H is negative, yeah, this is an exo what? Not just K-pop exo, this is exo what? Exothermic, that's right. So what we're saying here is highly exothermic reactions where the entropy value of the system is highly increasing. We've got everything in the right order. Reaction will be driven forward. Endothermic reactions where entropy is decreasing, not going to work. In a case like this, delta H is going the right way, right? The delta H is exothermic, but the delta S is holding you back. So it could be plus or minus. So where will it be spontaneous? High temperatures or low temperatures? If the T value is really, 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 really big, well, think about that. Remember, what's the goal? I want my delta G to be what? Positive or negative? Yeah, I want my delta G to be negative. My delta H is already doing its job. Delta S is the wrong sign, right? Delta S is negative. I want it to be positive because remember, it's the overall equation, delta H minus T delta S. If the T is large, the bigger the value that T gets, that negative delta S term becomes a problem. Remember, delta S is negative, minus a negative, positive value, so it could be positive or negative at low temp. Delta G will equal a negative value. And at high temp, or large values, delta G is going to equal to positive value. It means it's not going to be spontaneous at high temperature. It's only spontaneous at low temperature. This is what we describe as a enthalpically driven reaction. The reaction is happening because of the enthalpy term. It's the one that is helping the reactions be spontaneous. The thing that's holding it back is the entropy. Entropy is working against you here. So low temperature is actually your friend. Does anybody know of a case where this exists? Low temperature is actually good for a process and high temperature is bad. Have you guys run into one like this before? Well, computer temperatures, that's true. I wonder if that actually fits really well. You're right, lower temperatures generally help with semiconductors, that's true. Freezing, kind of, that's more that, you need to be at the melting temperature. But yeah, I wonder if that would also fit really well. The one that I've run into that's really, really weird, solubility. So generally, if I warm something up, if I heat up something, more soluble or less soluble, generally? Yeah, generally. There's a molecule, one that we've worked at quite heavily in our lab, called lithium carbonate. Lithium carbonate is the battery material you need to make lithium-ion batteries. It shows what's called an inverse solubility. At high temperature, it actually crystallizes. At low temperature, it actually dissolves. And because of this, what we're saying is the enthalpic term is a problem. At high temperature, the enthalpy term becomes so large, it drives the equilibrium back to our solid state. At high temperature, low temperature, the enthalpy term is minimized. The enthalpy is, I got it wrong. This is punch in the head time. Entropic term is a problem at high temperature, right? That's our negative T delta S. So at high temperature, entropy is causing it to crystallize. At low temperature, entropy is minimized. The enthalpic term, the delta H, is the one that is helping you now. So cases here where low temperature is your friend, we're saying that the entropic term is being minimized under those cases. And it's one where we've got this negative kind of value. So the last of the sequence, right? Last one, same. Here, let me just grab this. So once again, in our last one, if we did the last permutation, positive, this is again one of those cases where it could be plus or minus. And this is a typical one that we've run into before. This is one that's a lot more common, where you sort of have a temperature where everything's going to work fine and a temperature where it's not your friend. So here, at high temperature, what is it going to be? What's the sign of delta G? Yeah, at high temperature, delta G is negative. And what's happening here, right, is the delta S is going the right way. It's a positive value. That second term is our minus T delta S. And enthalpy is the thing you're fighting. It's an endothermic reaction that does not want to happen. So we have to make up for it by increasing or maximizing our delta S term. So that means at low temperature, the delta G value will be positive. It is non-spontaneous at low temperature and spontaneous at high temperature. Diamond formation follows delta H, delta S positive. Let me just remember that. In fact, I have to double check, because this is one of those cases where diamond is actually not the thermodynamic most stable state. Yeah, room temperature and pressure. That's correct. The joke being that everybody says that diamond is forever. In fact, diamond is slowly turning back into graphite, just floating around here at room temperature and pressure. It does not want to form under sort of room conditions. It's in fact at low temperatures here, the more stable allotrope of carbon is actually graphite. So anybody who sold you Berks, De Beers, whatever, said that the delta G, that diamond is forever. No, that is not true. That is kinetic. It is not thermodynamically true. So this is how we populate this table out. We've got these cases where absolutely it will always be spontaneous at all temperatures. We have cases that are always non-spontaneous. And this is where those two terms are both moving the same way to get you an overall negative delta G. And we have these other two cases where you're either fighting entropy or you're fighting enthalpy. Yeah, diamonds are under kinetic control. That's right. It could take you forever to, well, more than our lifetime on geographic scales. So what this just means is this is all reactions based on the thermodynamic parameters will fall into one of these four categories, and we can separate them out as individual ones. What's an example? Give me something that would say that if you had to give me a reaction that probably fits into that third category, spontaneous at all temperatures, what would something like that look like? If you, like we just said, maybe dissolution might be these two at high-low, this for first and third. Number three, what would be a good example of a reaction where we're pretty sure it's always spontaneous at all temperatures? You got to have a big negative, an exothermic reaction, right? And the entropy has to dramatically increase. So what do you think might fit that sort of category based on the things we've talked? Yeah, combustions or explosions, exactly. Explosive materials, you've got both things going towards you. A large release of heat. The delta H is very large and negative. And we also have a large production of gas, right? We've got a delta S for the system to be very, very positive. Everything is in the right direction to go like that. So these are spontaneous reactions at all temperatures. So again, this is one of the things that helps you to go through it, is trying to match these kind of parameters and what we're sort of talking through to things that you're sort of, again, match the systems of equations and stuff that you've seen. All right, so let me launch this one. Which combination of temperatures and pressures would give you an always spontaneous one? Excuse me, at a constant temperature pressure, which gives you a chemical reaction which will always be spontaneous. All right. So that, again, that follows what we just said. We're looking for something that has a large exothermic process. Delta H is negative, less than 0, and something where the delta S is going to be a positive value. We're producing moles of gas or changing from a solid to a liquid or something to that effect. So that is our context. Now what we're going to do is follow on this and say, look, we're going to use this concept, what known as the delta G, for a reaction in order to sort of rank or determine things about the overall energy changes during these processes. Now, again, the major difference with delta G is that we're going to now be focusing on processes that take into account both the enthalpic and entropic, the delta H and the delta S kind of terms. Now, the thing to measure, though, is we've got two different values. When we say delta G, or free energy, there's usually two things that we focus on. The delta G naught of a reaction is considered to be a standard state type change. You're saying, I'm starting at my starting material, it has some free energy at standard conditions, and I'm going to my product, which has a different free energy under standard conditions. So you can think of it like a level diagram, just like we've talked about before for like things like entropy and enthalpy, right? You start at some initial, you go to some final. What we call the delta G naught for that reaction is the difference going from all starting materials to all products. If we have a positive value under some conditions, we're saying that it's not possible or it's not spontaneous under the conditions we've applied. And we could have a case where temperature allows us to sort of fix this off. We could also potentially change things like pressure or other values to drive a reaction which may not be spontaneous. Not being spontaneous doesn't mean it does not exist. It means that we're really going to have to mess with the conditions or provide some other way, because again, we're talking about the delta H, delta G of a reaction. If delta G naught of a reaction is negative, yes, it's true that it is not a spontaneous process. It doesn't mean that it can't happen. We may have to engineer it by adding other stuff to this as well. But that's the first value. We call this the delta G naught of the reaction. We measure this again in the same way that we have before. If we have our standard Gibbs free energy, we can use the two terms that we've used before, our delta H and our delta S naught, in order to calculate what this value is at some given temperature. And it follows the same pattern we did with both Hess's law and standard free energies, right? Finals minus initials. The only difference here is usually you're not given just delta G's. You're usually given things like your heat of formation, so your delta H's, and your standard entropy values, your delta S's. So if we were given something like this, we can go through and calculate this in the same kind of formulaic way that we've done before. If we're finding this, we've got our individual different pieces, and we're saying, look, for this overall reaction, what are the thermodynamic parameters associated with this? How do we get to delta G naught? Now, what we've been given in this sort of table is our heats of formation and our enthalpy values. So we're going to go through and do it in a point-by-point way. Okay, so once again, we don't have initially our delta G. We want to know initially our delta H of this reaction. So it's going to be, as we've done before, our products minus our starting materials, final states minus our initial. And looking here, there's only two values, right? We are given hydrogen as a gas, sodium oxide as a solid to make sodium as a metal, sodium solid, and water. So if you notice, two of these values, sodium and hydrogen in terms of their delta H, have values which are 0. So the products we're doing here, this is our water value, so it's going to equal to minus 285.8 kilojoules per reaction, right? That's our this is our products minus our starting material. Starting material value here is our sodium oxide. That's 415.9 kilojoules. Overall, delta H for this reaction is equal to 130.1 kilojoules. What do we know about this so far? Endo or exothermic? Yeah, this is an endothermic process. The delta H is equal to a positive value. If this is going to be spontaneous, so far, what do we need to happen at this temperature and pressure? If this is going to be a spontaneous process, we've already got a case where delta H is positive. How does it have a hope at all to be a spontaneous process? Yeah, we got to have a big positive delta S, right? If that's negative, we might have a case. Now, again, look at the overall reaction. Back to the general sort of sequence of stuff that we're using. Do you think that's going to come up that way? We're hoping for a delta S of this reaction to be positive. Yeah, no, it doesn't look good, right? Why is this not going to happen? Why would you expect, again, going forward to the next step, why would you expect the delta S of this to be negative? Yeah, we're losing gas molecules, right? 2 molecules of hydrogen, or hydrogen H2 gas, has to turn into a solid and a liquid. So the delta S of this reaction is going to equal to, again, our products, and it's going to be equal to water. That's 69.9. Again, this is joules per mole. Kelvin plus our 2 molecules of sodium, 2 times 51.2. Again, joules mole Kelvin, minus all of our products. So that's equal to 130.7 joules mole Kelvin, and that's for our hydrogen, and our last value is our 72.8 joules mole Kelvin for our sodium oxide. Putting this all together, delta S of the reaction is equal to minus 31.2 joules per degree Kelvin per reaction. So if you notice on this one, this matches our expected value. It's an endothermic reaction. The delta S here is equal to a negative value. This is not going to be spontaneous. We can't use temperature alone under standard conditions to drive this reaction. What we're going to have to do is probably increase the pressure or something else to go outside of these standard conditions. What we're saying is under standard conditions, temperature equals 298, pressure equals 1 atmosphere. As we go through this part, we're not going to work out. The last thing, to get to our delta G, we're not quite done yet. The delta G of this reaction means, oh, that's easy. We just punch it into delta H minus T delta S. So what's the warning here? Why do I not take these values directly and just punch them in there? Mole is canceled. What I mean by mole is canceled here, and you could put mole back into the value here, kilojoules per mole. Remember, mole is one term over the reaction. That's entirely possible, right? Same thing here. I could refer to this as 31.2 joules per mole of the reaction. Remember, all we're just noting here is that this is one turnover of this reaction in that part. It's not a single molecular entity. It's one turnover, one starting material to product. Yeah, the big thing is enthalpy values are usually larger magnitude than entropy values. You are kilojoules and you are joules. Do not slam the values together and just calculate away. And to do your dimensional analysis, the temperature value we put in here, what unit must this T be in to finish this off? Yeah, it has to be in Kelvin. Again, that's located right here. The entropy value that we've calculated is in joules per degree Kelvin. So to finish this off, the delta H, we could look at this as 130.1 kilojoules per mole of reaction. And then it's minus T, 298 degrees Kelvin, multiplied by negative 0.0312 kilojoules per degree Kelvin mole of reaction. So I've chosen to express our joule value up here as kilojoules. You could do either, right? Either you bring your delta H into joules, or you bring your entropy value, your delta S, into kilojoules. Once we're finished with all that, delta G is equal to a positive 139.4 kilojoules per mole of reaction, or just kilojoules for one turnover of this reaction. But it's a positive value over here. Conversion factor, remember, joules to kilojoules, that's the same thing as like miles to kilometers, right? Yeah, by a factor of 1,000. Kilo. Yeah, that's it. Not miles to kilometers, excuse me. Meters to kilometers. Okay. So but what we know from this one in terms of its actual value and the value that we're expecting here is that, first of all, under these conditions that we've defined, this is not a spontaneous process by any temperature. We can't just change temperature to make this work. We're going to have to go outside of standard conditions, which generally for a guy like this would be pressure. If we pressurize the system, what do you think that's going to do to the delta S of hydrogen, right? If we compress it under super high pressure, what do you think that's going to help you or hurt you? Just by general opinion, what do you think would happen to this guy? It forces the reaction. It actually will help it, and we'll talk a little bit more, which we're going to jump off of next time. But there are, again, if you come up with something like this, where the delta G naught of the reaction is positive, all we're saying is there must be this step down in energy. My starting material's free energy total must be high. My product value, a step up. I'm starting at some free energy value and I'm going to a higher free energy value as denoted by these standard type conditions. We can still make the reaction happen, but we're going to need to do a lot of work. We're going to have to go way outside our standard conditions, which generally means modifying the temperature where this whole thing happens at and the pressure that's involved along with it too. But simply looking at this, if all we were trying to do is just tweak temperature, not change pressure, use the delta H and delta S that are provided here, there's no way that this reaction will ever happen spontaneously. All right, this is where we're going to stop today. We'll pick up this value here and we'll talk about the difference between delta G and delta G naught. Delta G naught being the overall reaction, delta G being a single value for some composition here. And that's how we get these sort of equilibrium processes to work. Thanks very much, guys.